So good morning students, once again welcome back to chemistry online classes. So in the previous class I told you in the lecture 14 that is molecular orbital theory, said features. Even I told you that is demerits or disadvantages or limitations of the valence bond theory. To overcome those only, this bond was given by FH and RS silicon, but later was modified by Slater and Pauling. Then I told you regarding linear combination of atomic orbitals method. Means two atomic orbitals of nearly same energy and proper symmetry, they will overlap to form molecular orbitals, leading to formation of bonding molecular orbitals and anti-bonding molecular orbitals. Bonding molecular orbitals are orbitals which are formed by addition overlap or addition wave functions, whereas anti-bonding they are formed by subtraction overlap of the wave functions. Okay, right. Like this I told you LCAO method, even with the electron density and with that is wave function picture also I shown you, and difference between bonding and anti-bonding molecular orbitals we have learned yesterday. Now let us go to today in the lecture 15, very importantly, rules for filling up of rules for overlapping of atomic orbitals. Overlapping of atomic orbitals. Overlapping of atomic orbitals to form molecular orbitals. Form molecular orbitals. Okay, right. See here, students. See, generally you know that two atomic orbitals of nearly same energy and proper symmetry, they overlap along internuclear axis, leading to formation of sigma molecular orbitals, and along the sideways to form a pi molecular orbitals. Yesterday that also I showed you the last 10 minutes shapes of the sigma molecular orbitals, bonding, anti-bonding, and even pi molecular orbitals, bonding and anti-bonding. Okay, now they will help you in understanding rules for overlapping of atomic orbitals to form molecular orbitals, or you can tell condition for overlapping of atomic orbitals to form molecular orbitals. First, okay, that is orbitals which are involved in okay, that is overlapping should not differ much in energies. Not much differ in energies. Means oneness atomic orbital can overlap with oneness not 2s atomic orbital. Okay, like this. Not only oneness should overlap with only oneness, but not 2s. Like this, 2p can be only 2px with 2px, 2py with 2py, 2pz with 2pz. Remember, but oneness cannot overlap with 2s or 3s. 3s cannot overlap with 4s. Like this, they should not differ much from one another. How? In terms of energies. Almost they should have equivalent energy. That's why I use the word equivalent. Right. Secondly, extent of overlapping must be high. Extent of overlapping must be high. Why? Higher the extent of overlapping, stronger the bond. Next, third one. they should have proper symmetry, and equivalent energy, which already once again I repeated the first one, proper symmetry and equivalent energy. Then fourth one, not only this, even lobes of atomic orbitals. Lobes of, very very important, lobes of atomic orbitals should be in proper orientation. The lobes of the atomic orbitals should have same sign, not in proper orientation, should have same signs, that is plus plus, minus minus for bonding molecular orbitals, and different, that is plus minus plus for anti-bonding molecular orbitals, okay, or by. And yesterday itself I told you that these molecular orbitals, when they overlap along internuclear axis, they form sigma molecular orbital, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, sigma star 2pz. Then next, if they overlap along sideways, they form pi 2px, pi 2py, pi star 2px, pi star 2py, bonding, anti-bonding. Right? So remember, always students, even the lobes, signs of the lobes also very important while overlapping. They should have proper orientation along with the, if they are having same signs, plus plus, minus minus, then they form bonding molecular orbital. They form plus minus and minus plus opposite sign. Lobes should have opposite signs. Then that's only yesterday I showed you in the shape of the orbitals. Okay. Favors bond formation, plus plus minus minus, does not favor bond formation. Phase in, phase out. That's what I given you yesterday, shapes of orbitals. Okay, these are the rules. Okay, that's about the rules or guidelines why overlapping atomic orbitals should form molecular orbitals. Got it? That means here 2px is to 2px, 2p not 2py. Proper orientation, that is also important. 2py should overlap with only 2py, not 2pz. 2pz with 2pz. 2px, 2px, 2py, 2py, 2pz, 2pz. But not 2s with 2px, or else 2px with 2py. It is not possible. They are phased out. That's why yesterday I given you with the shapes phase in, phase out. Right? Sigma as well as pi. So that's about rules for filling, not for filling, overlapping of atomic orbitals from molecular orbitals. Now after this, here you will study next the rules for filling molecular orbitals. The rules for filling the molecular orbitals. See, rules for filling molecular orbitals. Okay, rules for filling molecular orbitals, right? Okay. See here, what is first one? Outbound principle. That means these molecular orbitals, they also, okay, fill up, same as usual like the atomic orbital. They also follow three rules: Outbound principle, Pauli exclusion principle, Coulomb rule. Same what I explained you in the structure of atom. Okay, students, the Outbound principle, what it says? Electrons enter into various first one. And second, Pauli's exclusion principle. Pauli's exclusion. Exclusion principle. Okay. Molecular orbital can accommodate only two electrons. Only two electrons. These electrons cannot have values of all the quantum numbers same. Okay, all the quantum numbers same. Then if they will be same with respect to principal quantum number, azimuthal quantum number, magnetic quantum number, but the different spin quantum number. Same, no any change. Third, Hooke's rule. Hooke's rule of maximum multiplicity. In case of degenerate molecular orbital, molecular orbitals instead of atomic orbital or molecular orbitals. Electrons start pairing unless and until all the orbitals are singly occupied over and down. That means first they occupy upward then down. As usual, what we studied in this lecture of atom. Okay, that's about what it is. Rules for filling up a molecular orbital. They also follow same Bohr principle, Pauli's exclusion principle, and Hooke's. Got it? Okay. After understanding condition for overlapping of atomic orbitals to form molecular orbitals, rules for filling up of the molecular orbitals, which can be asked separately for 2 marks in the theory. For theory, you will ask it for 2. Then you have to write this as well. Okay. Right. Now coming to students, next. What is bond order? How bond order helps in predicting the stability of these molecules. After bond order, lastly we will go for energy level diagram. But before energy level diagram, we should know all these short notes. Okay. Right. The next concept is what, students? Bond order. Okay, so what is bond order? Bond order is just nothing but, okay, it is defined as definition is according to molecular orbital theory. Bond order is also studied in BBT, number of covalent bonds would exist between two atoms. But here, according to bond order is, it is defined as difference, one half the difference. One half the difference between the number of electrons present in bonding molecular orbitals PMO and anti-bonding molecular orbitals ABMO. It is defined as what? One half the difference between the electrons present in the bonding molecular orbitals and anti-bonding molecular orbitals. Therefore, mathematically, BO bond order is equal to 1 by 2 NB minus NA. NB minus NA. What NB stands for number of electrons. Number of electrons in short form I am just writing students, bonding, molecular or molecules. BMOs. And what is the name? Number of electrons. Number of electrons in ABMOs. Antibonding, molecular or molecular. Got it? Bonding molecular and antibonding molecular one. So this bond order helps us in what? Predicting stability of molecule. How does it helps in predicting stability of molecule? Let us see. Stability of molecule. Significance. Significance or importance in predicting bond stability if BO is equal to 1, that is greater than 0, molecule is stable. Molecule is stable. Remember, if bond order is less than 1, that is equal to -1. Okay, that is less than 0. Negative. And that is positive, better. And this is negative. Okay, less than 0. Molecule is unstable. If bond order is exactly equal to 0, then molecule does not exist. Does not exist. Means, see, if the bond order is greater than 1, positive value, molecule is stable. After calculation of this. If the bond order is negative, it is less than 0, molecule is unstable. If bond order is exactly 0, it is almost molecule does not exist. Means molecule will be there, but there is no covalent bond is present. In that case, they are held by weak van der Waals forces of attractions. Okay, that will come to know once again by calculating bond order, predicting stability. Even the calculating after predicting stability, after writing molecular configuration, you will also have to go for predicting magnetic property, because it was the demerit of valence bond theory. That also will tell. Okay, right. This is the significance of bond. If they ask you bond according to molecular orbital theory, it is defined as the 1/2 the difference between the number of electrons present in the bonding molecular orbitals and anti-bonding molecular orbitals. NB number of electrons in BMO, Na number of electrons in ABMO. Okay, that is the form. Just I will now show you afterwards one by. Okay, right. This is all about bond order. So this bond order, remember, I will tell you at the last. Already I told you, bond order is directly proportional to bond stability. Bond stability, even bond dissociation energy, but inversely proportional to bond length. Repeat. Bond order directly proportional to BDE, bond dissociation enthalpy, directly proportional to bond stability, but inversely proportional to bond length. Remember, bond length. Got it, students? Bond. Once again, I will explain you in detail this point also, while calculating bond order, even predicting magnetic property, and bond order calculation will come to know very clear. Right? Okay. This is all about the short notes of the bond order. See, this will help us indirectly in what? Predicting stability of homonuclear as well as heteronuclear diatomic molecules. Okay, and this theory is applicable both for homonuclear and heteronuclear. Let us see. Okay, after this, now switch on to very importantly energy level. Energy level Energy level diagram. Energy level diagram. What is this energy level diagram? Arranging various molecular orbitals. Arrangement of various molecular orbitals. Molecular orbitals according to their increasing energy levels. According to their increasing energy levels. Increasing energy levels. Okay, this is nothing but energy level. It's called energy level diagram. Okay, now I will show you one by one how they are. Very important point to be noted. We know sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Okay, we are aware of this. Then pi 2px, pi 2p, pi star 2px, pi star 2p1, bonding and then sigma 2pz and sigma star 2pz. These are the various only one available molecular orbitals. Okay. Now here I have to keep one convention in the mind. Up to atomic number 7, up to 14 electrons, 1 rule. After above 14, 1 rule. That's it. I will tell you one by one. You come to know clear. Right? First convention. Convention 1. What is that convention? For diatomic molecules, homonuclear diatomic molecules like H2, okay, He2, Li2, Be2, B2, C2 and N. Okay, follows the order. What is that order? Sigma 1s less than sigma star 1s. Sigma 2s less than sigma star 2s. Okay. Then pi 2px bonding, pi 2p. Before this, sigma 2p had. Then pi star 2px, pi star 2p1. Then lastly, sigma star 2p. This is the first convention. Next convention 2. Convention. That means this is up to atomic number 7 and 14 electrons generally. So greater than atomic number 7 for diatomic molecules. That is O2, F2 and neon. Okay. Follows the order, increasing order. What is that? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Okay, then before first only sigma 2p. Then pi 2px, pi 2py. Okay. Then pi star 2px, pi star 2py. Then lastly sigma star 2p. See, this is the difference here. Okay. Here sigma 2z orbitals comes after pi molecular orbitals. Here sigma 2z orbitals comes before 2pz orbital. Why sir? What is the reason? See students, before going to sketch the energy level diagram, first they have to by heart this. Sigma 1 is sigma star 1 is, sigma 2 is sigma star 2 is. First pi 2px, pi 2py, then sigma 2pz, then pi star 2px, pi star 2py, then sigma star 2pz. That means up to atomic number 7. If you double them, it will become what? 14. Right? What will happen here? Difference in 2px and 2py. Difference almost becomes very less due to small size. They are having what? Repulsion. That's why sigma 2pz is having more than this pi 2px, pi 2py. Difference is not so much. Okay? That's why if the difference is not so much, that is responsible for what? Hybridization. That's why I told you almost equivalent energy. That's why sigma 2pz is having more energy than pi 2px, pi 2py. But greater than 14, that means above 14, above atomic number 8, above atomic number 8. Here, difference between 2px and 2py almost become more. Gap will be more. If the gap is more, overlapping will be less. That's why sigma 2pz will be having less energy than pi 2px and pi 2py. They come before pi 2px, pi 2py. This is the only thing. But remember, always 2pz will form sigma, 2px, 2py will form only pi overlapping or pi molecular orbitals. That's it. Even this you can use in hybridization also. So 2pz means always, okay, that is head-on overlapping. Okay, axis. But 2py, 2pz lie perpendicular. Sorry, 2px, 2py lie perpendicular. They form pi bonds. Please be very clear. I mean, repeating students, please have to remember this convention. That means this is valid for above hydrogen to nitrogen. That means atomic number 1 to atomic number 7. And above atomic number 7, you have to follow this. Okay, due to the reason I told you. Here, difference between 2px, 2py is less. Therefore, sigma 2pz will be having less energy. But here, difference is more. Sigma 2pz will be having less energy. That's it. Okay. Now, keeping this in all in the mind, now we will go for sketching one by step energy level diagram for hydrogen, helium, okay, then lithium. These are foreign elements. Then boron, beryllium is not there, but still I will show you. Then carbon, nitrogen, oxygen. We have to use this mod, sketch the energy level diagram, calculate the bond order, predict the stability, predict the magnetic property. Okay, I'll tell you, generally if upon writing molecular configuration, if there are no any unpaired electrons, it is called as diamagnetic in the nature. If at least one unpaired electron is present in the outermost valence shell, then they are called paramagnetic substances. Paramagnetic, at least one unpaired electron. Diamagnetic, no unpaired electrons. If the number of unpaired electron increases, then that is called ferromagnetic. Generally that will not arise here. Maximum the molecules may be classified as what? Diamagnetic, no unpaired electrons. Paramagnetic, at least one unpaired electron. Okay? Right. Let us see. With all this discussion now, I will try to apply more in sketching energy level diagram for homonuclear diatomic molecules with all these concepts. Okay? I will show you now. We will come to very clearly. All the doubts will be clear. Application of bond order. How bond order will done was in determining step. See the first sketch the energy level diagram. Energy level diagram. Energy level diagram for hydrogen molecule. Before going this one, actually what is the energy level diagram? Sorry, I have not told you how to draw this. See here. First, this is sigma, this is atomic orbital. Okay. Molecular orbital. These are outside oneness, oneness. Atomic orbital. Atomic orbital. This is sigma oneness, sigma star oneness. These are called molecular orbitals. Molecular orbitals. Bonding antibonding. That means two atomic orbitals of nearly same energy and proper symmetry. See, oneness, oneness. They mix up to form sigma oneness, sigma star oneness. Bonding antibonding. Like this. Next, same way, 2s. You can show me. Okay. You can show. This is 2s, 2s. Okay. Sigma 2s, sigma star 2s. Okay, then very importantly, first this is sigma orbitals. Outside 2p, 2px, 2py, 2pz. Okay. Here also same thing. 2px, 2py, 2pz. 2pz. Right? Now here in between you have two dabbas, that is important. This is sigma 2pz. This is called sigma star 2pz. Pi 2px, pi 2py. Bonding. Antibonding. Pi star 2px, pi star 2py. Actually, this is the first without convention. This is actually increasing energy level diagram. Sigma 1 is sigma star 1. Sigma 2 is sigma star 2. Right? Then actually pi 2px, pi 2py, pi star 2px, pi 2py, sigma 2pz, sigma star 2pz. Because here only we are interchanging. Up to nitrogen, sigma 2pz first here, then pi 2px, pi 2py here. Above nitrogen, sigma 2pz will go, come back once again here, and 2px, 2py as well. That will come to know one by one when I will show you how to fill up using Aufbau principle, Pauli's exclusion principle, and Holmes rule. Because this is very much confusion, that's why I will make it clear one by one. Okay, and this is energy level diagram. See this arrow mark I will show what it shows: energy, energy, right? Increases. If you go compass side, right? Energy increases from lower to higher. You should not draw first this one. This is wrong. This is only correct. First 1s, then 2s, then 2p. In 2p, 2px, 2py, 2pz. That's only 2px, 2py. They form pi molecular orbitals. And sigma 2pz will form sigma molecular orbitals. Got it? This is the background of energy level diagram. So now I will show you one by one with the questions how they will ask you in the examination. Then you will come to know very clearly. See students, question they will ask you: sketch energy level diagram. Energy level diagram for hydrogen molecule. Okay, calculate bond order. Calculate bond order and predict magnetic property. Predict magnetic property. Magnetic property. See, hydrogen molecule here. You know that hydrogen molecule is obtained by combination of two hydrogen atoms. Normally, atomic configuration hydrogen molecule 1s1. But hydrogen molecule it is 2 electrons, therefore molecular configuration for hydrogen is sigma 1s, sigma star 1s. Compulsory students you have to write this. Bonding antibody. How many electrons are there? 2 electrons. Both electrons first enter into bonding, then antibody. Antibonding? No, 0. Right? Okay. Then what is the bond order? Bond order is 1 by 2. Nb minus Na. Nb minus Na. What are bonding electrons? Without star, these are bonding electrons. Antibonding is star, asterisk, that is 0. So 1 by 2 into 2 means what you will get? 1. Bond order 1 greater than 0. It is stable. Okay, hence hydrogen exists as hydrogen molecule. Hydrogen molecule exists as H single bond H. Single bond. See, after writing molecular configuration, this is what here. Are you finding any electrons here? No. No unpaired electron, therefore it is diamagnetic. Diamagnetic. Since there are no unpaired electrons. No unpaired electrons. Okay, after calculating bond. Like this thing. Stability will help us in predicting bond. That means hydrogen atom they are held by single covalent bond. And already know imbalance bond theory. Okay, now energy level diagram. Only one. See, this energy level diagram is purely we have to draw only on the basis of molecular configuration. This is very important. How we write a single atom atomic configuration? This is called molecular configuration. How many? Only 2. So draw here sigma 1s, sigma star 1s. Got it? Outside, what do you draw? Atomic orbitals. Okay, atomic orbitals. 1s, right? And here 1s. Right? Atomic orbitals. And these are bonding molecular orbitals. Bonding and debonding. Now see electrons, where are they? Outside. 1s. 2 atoms they overlap along the intermediate axis forming sigma bond. Where they enter? Here. And here. This is the energy level diagram. For what? Hydrogen molecule. Like this, they will ask for 2 to 3 marks in the examination. Sketch energy level diagram. Okay, for hydrogen, helium, lithium, carbon, nitrogen, oxygen. These are for your syllabus. Okay, and calculate bond order and predict the magnetic property. If you are observing no any unpaired electron, diamagnetic. At least one unpaired, paramagnetic. Okay, so like this thing. Without star bonding, with star anti-bonding. This is first example of what? That is application of model. See what you studied, all we have applied. Got it? Okay. Now next question. Sketch the energy level diagram for helium. Next one. He2. Calculate bond order. Predict magnetic property. Predict the magnetic property or explain non-existence. energy level diagram. This is a question. Now see here, students will go on checking here itself. Our next molecule is called helium, He. In one helium atom, how many electrons are there, बच्चों? 2. Helium atom कितना हो गया? 4. So 4 electrons. First then there will be sigma 1s2, then sigma star 1s2. Got it? So this is over and out. Now BO, NB minus NA. These are now bonding. These are anti-bonding. So 2 minus 2. And the bond order कितना हो गया? 0. Since bond order is क्या लिखते हैं? Since bond order is 0, molecule does not exist. See, this is how. See, explain non-existence. Means what does not exist. That means in hydrogen and in helium, covalent bond is not present. But how they are present, sir? They are monoatomic. They are held by predominantly weak van der Waals forces of attraction. Remember, all noble gases. Got it? There is no covalent bond in noble gases. That's why, see, molecule does not exist. Molecule does not exist. तो खुलूस से नहीं उड़ेगा वो. Okay? Molecule वही रहेगा, मगर उस molecule के बीच, atoms के बीच में covalent bond नहीं रहेगा. Okay? But it is held by weak van der Waals force of attraction. Please try to remember non-existence का meaning. Okay, then energy level diagram as usual. Sigma 1s, sigma star 1s. निकालो. Outside क्या है? 2 electrons. इधर पेयर हो गया. देखो इधर पेयर हो गया. According to Hund rule, Hund's rule. पहले क्या था? सिंगल ही ऑक्युपाई, एकांगी. बाद में क्या हो गया? द्विकांगी, पेयर हो गया. Right? अब ऐसा ही इधर 2, total 4. 2 they will overlap to form bonding, anti-bonding. Total 4 electrons. This is the what second example? Second example of what? That is energy level diagram. Non-existence of helium molecule. Very, very important. Really, very important for theory purpose for 2 months or 3 months. Last year you have to answer this. Okay? Very simple. Now just lastly, I will try to wind it up by explaining another one last example. Sketch the energy level diagram of lithium. Light. Calculate bond order, predict magnetic property. This is, are you finding any unpaired electron? No. It is also what? Diamagnetic. Since there are no any unpaired electrons, it is diamagnetic in the nature. Got it? No unpaired. If they are all paired, diamagnetic, no unpaired. If they are paired, if they are unpaired, then it is diamagnetic. At least one. Okay. Now coming to next example, lithium. Li2. Atomic number of lithium you know 3, but Li2 3 plus 3 6. So molecular configuration sigma 1 is to sigma star 1 is to this is important. Now you will see sigma 2s sigma star 2s कंपल्सरी बॉन्डिंग एक बार लेगा तो इसके साथ इसका एंटी बॉन्डिंग लिखना है. एंटी बॉन्डिंग भी कंपल्सरी लिखना. ओके, तो क्या हो गया? सिग्मा 2s भर गया, सिग्मा स्टार 2s 6 इलेक्ट्रॉन ही है 0. दिस इज वेरी इंपॉर्टेंट. तो बॉन्डिंग कितना है बच्चों? देखो 2 और 2 4. एंटी बॉन्डिंग स्टार याद करना है. एंटी बॉन्डिंग कितना है? 2 है. तो बॉन्ड ऑर्डर क्या हो गया? 2 कैंसिल हो गया. ये तो बॉन्ड ऑर्डर 1. सेंसर बॉन्ड ऑर्डर greater than 0, stable. And see here, lithium, it exists. How lithium exists? Lithium single bond lithium. Okay, and what it is? Are you finding any unpaired electron? No, all are paired. Diamagnetic in nature. देखो bond order, stability, magnetic property धनात्मक बिगना है. Next see here, energy level diagram के लिए जरा इधर सर्कस करना. एक बिल्डिंग आप ऑलरेडी लिखे, सिग्मा 1 है, सिग्मा स्टार 1 है. अब क्या है? दूसरा बदला स्टार्ट है. अब 2s सिग्मा स्टार्ट है तो क्या करना, और एक डब्बा और एक ब्लॉक को खड़ा करो, तो क्या करो 2s कहो और इसको भी इस साइड 2s। एटॉमिक ऑर्बिटल का पूरा हो गया। क्या करेंगे नेक्स्ट, ऑलरेडी सिग्मा 1 है सिग्मा स्टार है, इधर क्या लेते हैं सिग्मा 2s सिग्मा स्टार 2s, तो क्या लिखेंगे 2s, राइट। नाउ सिग्मा 1s to सिग्मा स्टार ऑलरेडी भरे हैं, सिग्मा 2s को इधर नहीं 0, इधर आउटसाइड एक एक इलेक्ट्रॉन, सी 3 plus 3 6 2 4 6 9, वेरी गुड। दिस इज एनर्जी लेवल डायग्राम। उसके बाद क्या करो, झंडा ऊंचा करो, this that compulsory have to show, this shows increase in energy level. This is the last step for lithium molecule. That means today I have explained very important less than 7 hydrogen I covered, helium I covered and lithium. Okay, so we'll stop here. So tomorrow's class, last week I will wind it up, this molecular orbital theory. I will explain you carbon, nitrogen, oxygen, okay, and how we have to use that convention, both two important convention that will come to know very clearly tomorrow. Until that you have to work, okay, you have to be very calm and you have to just wait for that. Okay, then lastly hydrogen bond, covalent bond, that will be the completion of chemical bonding. Tomorrow or day after tomorrow definitely I will complete it. Okay, so enjoy, have a nice day, and this is from PANCHNATH. Have a nice day. Thank you.